Ever pause to wonder how electricity travels from the power plant to your home appliances? It's easy to overlook this, isn't it? We live in a world where a simple flip of a switch illuminates our homes, a gentle tap on a screen connects us with people thousands of miles away, and a press of a button prepares our meals. These everyday conveniences are powered by an unseen force that works tirelessly behind the scenes: electricity. Electricity is a crucial part of our lives. It's the lifeblood of our modern world, powering everything from the smallest microchip to the largest city. But where does this incredible energy come from? The journey of electricity starts at power stations. These are the heartbeats of our electrical world, where raw energy sources like coal, gas, water, or the sun are converted into electrical power. These power plants are like massive generators, creating electricity by moving a magnet near a wire to create a steady flow of electrons. But what exactly are electrons, and why are they so important in this process? Well, you can think of electrons as the tiny messengers of the electrical world. They carry the energy from the power plant to your home, speeding along wires at nearly the speed of light. In a nutshell, electric current is the flow of these electric charges, these electrons in a conductor. It's this current that powers our world, allowing us to have light at the flick of a switch or enjoy a hot cup of coffee at the press of a button. But it's not just about the electrons. The wires they travel along are also crucial. These wires are made from materials that allow the electrons to move freely, conducting the electric current from the power plant to your home. Intriguing, isn't it? How this invisible power makes our lives so convenient. It's a journey of science, innovation, and a testament to human ingenuity. But it's also a journey that's just beginning. As we move forward, the ways we generate, conduct, and use electricity will continue to evolve, shaping our world in ways we can't even imagine yet. But how does this electric charge find its way to your home, you may ask? The answer lies in the role of certain materials known as conductors. These materials, particularly metals like copper or aluminum, have a unique superpower. They can transmit electricity. But how do they do it? Well, it all comes down to the behavior of tiny particles known as electrons. You see, every atom of a conductive material has a cloud of electrons that hover around the nucleus. These electrons are free to move around, much like birds in the sky. When an electric charge is applied, these electrons start to drift in the same direction. This movement of electrons is what we call an electric current. Think of it as a marathon race. The electrons are the runners, and the energy source, such as a battery or a power plant, is the starting gun. As soon as the race begins, the runners or electrons start moving in the same direction. They don't move very fast, mind you. In fact, their speed is only about a few millimeters per second, yet the effect is almost instantaneous. Why? Because when one electron moves, it pushes on its neighbor, creating a domino effect. This is how an electric signal can travel at nearly the speed of light, even though individual electrons move quite slowly. But there's one more piece to this puzzle. To keep the electrons moving, they need a little push. This is where the energy source comes in. Just as a runner needs energy to keep going, the electrons need an energy source. This energy source pushes the electrons along the conductor, keeping the current flowing. It's like a constant wind at the back of our marathon runners, urging them forward. So the next time you flick on a light switch or charge your phone, think about the amazing journey those electrons have taken. From the power plant, through miles of conductive material, all the way to your home. And remember, it's all about giving electrons a little push. Now imagine these electrons are commuters. What do they commute on? Wires. In the bustling city of electricity, wires are the busy roads, the veins of the system ferrying electrons from point A to point B. But not all roads are created equal, and the same goes for wires. The material of a wire plays a pivotal role in how well it can conduct electricity. The term we use to describe this is electrical resistance, a measure of the degree to which an object opposes the passage of an electric current. The lower the resistance, the smoother the journey for our electron commuters. Metals, particularly copper and silver, are common materials used for wires due to their low resistance. They're like the high-speed autobahns for our electron travelers. However, just as we encounter roadblocks and traffic on our commutes, electrons too face challenges. When electrons collide with atoms in the wire, it causes resistance and generates heat. This heat is essentially wasted energy, something we want to minimize in our electricity transportation system. That's where wire insulation comes in. Insulation is like the protective layering on our roads, preventing accidents and ensuring smooth transport. In the case of wires, insulation prevents energy loss by reducing the amount of heat generated. It also helps to prevent electrical shocks and short circuits, acting as a safety barrier between the electric current and the world outside. But what about those massive power lines we see stretching across the landscape, you may wonder? Those are mostly made from aluminum because it's lighter and cheaper than copper, while still being an excellent conductor. However, these wires are thick and heavily insulated to handle the high voltages they transport. So, whether it's copper wires in your home appliances or aluminum power lines zigzagging across the country, these pathways of power are fundamental to our modern world. They ensure that electricity, this incredible invisible force, gets to where it needs to go, powering our lives. Just like highways for cars, wires are the highways for electricity. But how does this electricity reach every single house in a city or even a country? That's where the magic of electrical grids and transformers comes into play. An electrical grid is like the nervous system of a city or a country. It's a complex network of power stations, transformers and transmission lines, connecting power plants to our homes, offices and factories. This grid ensures that electricity is always available whenever you need to turn on a light, heat up your dinner or charge your phone. Now let's talk about transformers. No, not the Autobots and Decepticons from the popular franchise. These transformers are specialized devices that adjust the voltage of electrical power. Why is this important? Well, it's all about efficiency and safety. Imagine you have to move a large quantity of water from one place to another. You could use a small pipe, but it would take a long time and a lot of pressure. But if you use a larger pipe, the same task becomes much easier and faster. The same principle applies to electricity. High voltage allows electricity to be transmitted more efficiently over long distances. But here's the catch. High voltage is not safe for everyday use. You wouldn't want to plug your laptop into a high voltage line, would you? This is where transformers come in. They step down the voltage from high to a safer, usable level for our homes and devices. On the other hand, when electricity needs to travel long distances from the power plant, it needs a boost. Transformers step up the voltage, allowing it to travel these great distances without losing too much energy. So the next time you switch on a light or charge your phone, remember the intricate dance of electricity. From the power plant, through the grid and transformers to your home, it's a journey of many steps. Just think about it, a whole network dedicated to feeding your home with power. Finally, the journey ends at your home, but how, you may ask? Well, let's trace the last leg of electricity's exciting voyage from the grid to your gadget. After electricity has been transformed down to a safe voltage at the local substation, it's ready to enter your home. A thick cable, often buried underground, carries this electricity from the substation to your home's electrical service panel, commonly known as the breaker box. This panel is like a grand central station for electricity, distributing power to different circuits within your home. Each circuit within your home is a separate pathway for electricity, designed to power a specific set of outlets or appliances. When you plug in your hairdryer or turn on your coffee maker, you're tapping into one of these circuits. The electricity travels along the circuit's wiring, which is typically made of copper or aluminum due to their excellent conductive properties. But what happens when too much electricity tries to rush down a circuit at once? Imagine a highway during rush hour. Too many cars can cause a traffic jam. The same principle applies to electricity. Too much current can cause wires to overheat, potentially leading to electrical fires. That's where our trusty circuit breakers come in. Circuit breakers are like vigilant traffic cops, monitoring the amount of current flowing through each circuit. If they detect an overload, they trip or shut off the circuit. preventing damage and keeping you safe. It's a vital role in the electrical safety system of every home. So the journey of electricity is a complex yet fascinating one. It starts at a power station, travels through transformers, along miles of power lines, through circuit breakers, and finally into your home's wiring. It's always ready to power up your gadgets whenever you need it. And just like that, with a flick of a switch, you harness the power that traveled miles to reach you. Isn't it amazing to think of the journey that each spark of electricity makes every time you turn on a light or charge